It's nice to see you again during our Interact 3 online lesson. And this time we're going to talk about cold. How do humans, and including polar researchers, cope with cold? I know that we had a previous lesson dedicated to animal adaptations to cold, an extreme cold, extreme weather conditions, but this time I would like to focus on humans, including polar researchers, and look at it from a little bit different perspective, hopefully. So let's start with basics. What is range of tolerance and what is our optimum range? Is it possible to live outside the range of our tolerance, our ecological tolerance? So changes in the intensity of some external abiotic factors affect the functioning or living organism, and they determine their occurrence and in the given environment and whether they're thriving or not. So if these changes fall outside the range of so-called ecological tolerance, so the organism perishes. Sometimes immediately, sometimes it takes a little bit time. It depends on the factor. So this ecological tolerance is the ability of the organism to adapt to changes and to the intensity of abiotic factors that are affecting it. And this adaptation ensures that we or other organisms can survive and carry out its vital functions, including breeding, for example. But within this tolerance range, there is a range of values, and these values can be temperature, humidity, and etc. So within this ecological tolerance, there is so-called optimum. So the range of values in which the organism functions functions best, so thrives, essentially. Some terms to start with again, so and two laws that I'd like to mention. So the first one is so-called Shelford's law, that which basically says the same, that if the too low or too high intensity of any given factor causes that organism can no longer survive in a given environment. And another very interesting law I'd like to mention is so-called Liebig's minimum law. So the Liebig's minimum law, or law of the minimum, is a law stating that the limiting factor in functioning of an organism in a physiological process is the level of which most closely approximates this margin value, and so the most deviates from the optimum value. So to explain it better, so we can have access to food, we can have access to water, but if we don't have access to oxygen, or it is very limited, then no matter how much food or water we have access to, the oxygen levels will be limiting factor. So it's also, of course, it's a combination of factors that affects our functioning, but on the other hand, there's always this one factor that is, we might say, critical. Some record holders, especially in terms of temperature, that we can meet in the animal kingdom, especially in polar regions, are, for example, polar fox and other, exactly like other animals. They have a range of adaptations like shorter paws, shorter tail, short muzzle, smaller ears, that are adaptations to lower temperatures, but that is a different factor. So here on the photo we also see Edredon, a duck, which has a different adaptation. So also to very low temperatures, it has very valuable feathers that allow them to keep them warm and also to keep their eggs warm. So another thing, species in general can be divided into stenobiontic and aerobiontic types of species. So stenobiontic are much less resilient. So they thrive very specific set of factors, set of conditions, but outside of them, they're not able to survive. And aerobiontic are much more tolerant, we might say, but also usually less specialized. So what are those limiting factors? I mentioned oxygen, food, and water, and this is so-called rule of threes, 3-3-3 rule. Air, water, and food. So we can survive without air about for 3 minutes, more or less. That's very individual. 3 days without water and 3 weeks without food. Again, these are this is an average, of course. But in case of humans, we with development of civilization, starting with fire and ending with central heating, air conditioning, etc., fridges, clothes, our insulated houses, we have become accustomed to rely on technology, which makes us a little bit independent of external conditions. It enables us to inhabit very friendly areas of the globe, even all year round, even Antarctic, winter and summer. Of course, there are no countries, no populations. The population actually living permanently in the Antarctic, but there are researchers who live there. But thanks to technology, thanks to technology that allows them to push the boundaries. Coming back to those record holders we saw on this slide before, sometimes we rely on natural solutions like these edgerton feathers are very, very valuable. That they can be used as filling of natural duvets or pillows that are very, very expensive. I mean, the cost of such a duvet filled in with natural material is between 6,000, even up to 30,000 euro, and they're better. They provide better insulation than any kind of man-made material, and also ultralight. So our technology sometimes tends to mimic natural solutions, and also sometimes natural solutions are very, very are not that are better solutions, right? We haven't learned to surpass the natural solutions yet in some cases. So do we cope more easily with heat or with cold? Of course, it depends on the intensity of these factors, but in general, and how extreme they are. Both extreme heat and extreme cold are able to kill us pretty fast. But actually, we are more adapted to endure cold for a longer time than extreme heat. Normally, you would be killed within minutes by heat. By temperature of 60 Celsius degrees, and for cold -40. Of course, there aren't any experiments that are conducted this way to observe when a human dies. We do not expose people to such conditions for a long time for the sake of experiment. But this is more or less, these are more or less our boundaries. Of course, given that we're only humans equipped with what we have, not with those technologies. So for the individual, we are more likely to tolerate frost for a long time. The extreme heat will kill us sooner than the cold, because we have mechanisms of thermoregulation, and we'll come back to that a little bit later. You do know that in general polar bears do not hibernate, but other animals, maybe surprisingly not necessarily living in polar regions, but living in more moderate climate, they do use hibernation. They do hibernate during unfavorable conditions, for example, during winter. Maybe not that surprisingly, because in polar regions they would have to maybe hibernate all the time. They do slow down their metabolism, but they do not hibernate, such like, for example, brown bears do in Europe. But can humans hibernate? That's a tricky question. That's a tricky question, and now it is believed that early humans may have hibernated to survive harsh winters. It's not set in stone fact, right? It is suspected that early humans may have done that, as some animals do nowadays. This is according to scientists who studied a very specific archaeological site in Spain, and they admit they are aware that such hypothesis may sound like science fiction to many. But how did they come to this conclusion? They examined some fossilized human remains found in a cave in Spain and in the mountains, and they were studying using microscopes, and discovered that the bones that were more than 400,000 years old had some fractures, lesions, other damage similar to what can be seen in animals that hibernate nowadays. Is it the final proof? No, but it indicates that early humans, very early humans, may have had this ability, because it's not something that you can control. They may have had this ability to hibernate, at least to some extent. But what about today? Well, there are some confirmed stories that are well documented, which may sound like a total clickbait and be totally unbelievable. Some are really astonishing, but like I said, they're well documented. So first, what we see on the slide is a photo of a man from Japan, Mitsutaka Uhikoshi. I hope I pronounce it without too much pain to the ears. In 2006, I believe, he went for a barbecue with his friends, and it took place in the mountains. So instead of taking a car back, on the way back, this guy, I think he was a official, like a very serious person. He was 35 years old at the time. So he decided to go for a walk instead of taking a car in the forest. But he didn't even, he got lost, but he stumbled, he broke his pelvis and was found, but he was found 24 days later. And body temperature was confirmed to be 22 degrees, 33.6 like normal temperature. So he was practically unresponsive, and he had zero metabolism, or close to zero. But he wasn't dead. He wasn't dead, and he survived. And it is believed that the mechanism, some sort of mechanism to protect, especially his brain cells, was triggered, because he did not suffer too much damage to his brain. So he survived. He was warmed up and he survived 22 degrees. And 21 degrees is believed to be like a level of complete, of being pronounced dead, right? And the other story is about a child. Children tend to be very much resilient. It's a little older story. It took place in Canada in 2001, but still not that long ago. And it's also well documented. So this is a story of Erika Nordby. She was 13 months 13 months old at the time. She was wearing only a nappy, and she escaped. She went out from home through the unlatched door. And it was in Canada, in Edmonton, and it was winter, and the temperature was minus 24 degrees Celsius. And she was found after a few hours. It was not as long as in case of this Japanese guy. And she had been technically dead for 2 hours, no palpable pulse, and her temperature was, hard to believe, 16 degrees. Like I said, 21, pronounced dead. Yet her heart had resumed working after she got a heating blanket. She survived, and she had some damage, but without any major health problems. So were they hibernating? More and more scientists are inclined to believe that we have some mechanisms. Maybe some of us, or for some of us, they are more developed. That are triggered and that are related to bacterial mitochondria that play a huge role here. So probably the current state of knowledge, at least, allow us to conclude that we had a common ancestors billions of years ago, that the bacteria merged with eukaryotic cell. And somehow, for some reason, it became like trapped in this cell. And this is what we got from this one cell ancestor. And this is some sort of, maybe this ancestry is more developed in some humans than others, because there are many stories of people who just froze to death. But in some cases, maybe there's mitochondrial activity related also to some chemicals. I don't want to get into details too much, can save our brain cells and allow us to be revived even after our body temperature drops under this magical barrier of 21 Celsius. Where do we come from? And because we're talking about ancestors, we'll be talking about them a little bit more. So the common knowledge is it all started in Africa, and it is no coincidence. I mean, it all started meaning humankind. It is no coincidence that our origins, our roots, are in those areas around the equator. Why? Because our ancestors, remember, had no clothing, had no fire that they could control, they had no shelter, and they had no choice. Their only chance was to live in conditions close to so-called thermic neutral point, this optimum I mentioned in the very beginning, right? Thermal equilibrium point for humans is about between 23 to 27 Celsius degrees. So in this thermic neutral point, we need to put no extra energy, neither to warm ourselves up or control the heat. We don't need that. So between 23 and 27 is more or less our TNP, thermic neutral point. So that was perfect. So the area is perfect, and the area around the equator was ideal in this respect, especially as the differences between the warmest and coldest periods are minimal. So small diurnal and small annual amplitudes of temperature. So, but why did we have to move away, at least, or expand? There are several theories. Was it only a call for adventure? Maybe, but more likely it was climate change and the drafts there. So our ancestors were forced to leave this comfortable thermal neutral point because of the drafts. However, after leaving the warm regions, our ancestors suddenly have to face some cold, continuous cold, or at least in some periods. Unfortunately, our evolution never sleeps and responded with some adaptations. So both behavioral and biological adaptations contributed to our success in surviving in very extreme climatic conditions, including cold, including high altitudes, even strong UV radiation, and so on. So that was a pressure. This is how evolution works. The pressure were those conditions. The pressure was confronting them, and there were some genetic variations resulting from varying metabolic efficiency, varying resistance to pathogens, even preferences of potential partners, mates. And here's where natural selection mechanisms kick in, resulting in some adaptations and new phenotypic patterns in humans. One of the mechanisms that is best known is thermogenesis, and here we can see three types, three methods of thermogenesis. So the human body, has two basic types of methods of thermogenesis. Thermogenesis meaning heat generation to raise body temperature, obviously. So the first one is shivering. And shivering occurs if we are not clothed and when the ambient temperature is below 25 Celsius degrees. So we start to shiver. Of course, it is modified by our clothing, but by our shelter. But if we're totally uncovered, our body starts to shiver, starting below 25 Celsius degrees. So there are, depending on how the cascade of these reactions leading to heat production, to raising temperature is triggered, we can further distinguish between different types of thermogenesis. So this shivering is like muscle tremor, which is uncoordinated totally, and which is either sweatless, meaning it is induced by the activity of brown adipose tissue, or caused by eating something warm. The actual word is postprandial, so it means it is after a food intake. It's not only that we feel warmer if we eat a hot soup, for example, just because there is intake of something warm into our body. There is a mechanism of postprandial thermogenesis, and this is the increase of heat production by the body itself. So it is dependent on the amount of type of food consumed, of course, but it's a large part of our energy expenditure daily. So the production of heat is associated with increased consumption of energy, which is required to digest this food that we ate. So theoretically, even if we eat ice cream, we need to digest them. So we produce more energy to digest them, and this is why we should be warmer. We produce more energy. So it doesn't have to be warm meal, but warm meal is of course preferable in such conditions. But do all humans feel the same about cold and warm? No, I think that we all know someone who thrives in the summer, and others hate the summer, hate the heat wave, and enjoy the winter and snow. So it is very much individual, but is it also related to like our race or ethnicity or something like that, or nationality maybe? So there was an experiment in the 1950s, scientific experiment, and the scientists were interested in adaptations and different response of different people to being exposed to different temperatures, being exposed to cold. So there was a group of volunteers, including Norwegians and Caucasian white people, Inuit people, and Sami people. And all of them were subjected to experiment while they were asleep. They were tested for the reaction while sleeping, but sleeping at very cold temperature, 0 to 6 degrees Celsius degrees. They were sleeping in sleeping bags. So white Caucasian Norwegians, they were unaccustomed to this. So they did not take the experiment very well. They were shivering all the time. As a result, they had elevated metabolism. They had very chilled skin. So, and the indigenous inhabitants of the Arctic reacted differently. The Inuit people did not shiver. There was not this muscle reaction. So their metabolism remained normal. But they slept restlessly. They did not sleep well, because under normal conditions they are used to be sleeping comfortably in the traditional igloos, which provide better temperature conditions, and also in clothing made of extremely warm materials, polar bear fur, sealskins that provide them protection. So they were not used to it. And the Sami people are accustomed to more nomadic lifestyle. And their traditional clothing is less extreme. I mean, they also use the polar materials, natural polar materials, but they're less extreme. They're the Inuit people, and they responded best. So the metabolism level remained the same, and also they slept sound, which would mean that we can get accustomed to certain extreme conditions, but in a long period of time, right? Because this is their lifestyle for generations. And accustomment would mean evolutionary mechanisms, right? One interesting fact, maybe to me, that contributed to the fact that someone might not have slept sound during the experiment, how did they measure their metabolism level? So during the study, they had their heads in boxes to test the intensity of their breathing, the content of the gas mixture in the box. So it may have been not that comfortable, but all the same, they had the same conditions, so their reactions could be compared. So what kind of morphological and physiological adaptations provided by this natural selection evolution mechanisms can be observed? So first, fat. Fat plays a big role not only in the diet, also is like a building element of our bodies, whether we like it or not. And each of us has two types of this fat tissue, so-called adipose tissue. So-called white adipose tissue, WAT, and brown adipose tissue, BAT. So the white adipose tissue is like a normal fat. It stores energy, but it also protects internal organs, and it's also like insulation material, but it's a passive insulation material. Brown tissue, instead, is responsible for maintaining body temperature and distributing it throughout the body. And the cells are built a little bit differently, but in general, it's like an active tissue. It has numerous mitochondria. And due to the presence of mitochondria, those small cellular thermal power stations, this BAT, brown adipose tissue, is characterized by great activity, and it takes care of body's thermoregulation. So we all have both types, but most brown tissue is found usually in newborn babies, so they can be kept warm after the birth. And with age, the tissue, the brown tissue, disappears, and in adults, it is mainly located along the large blood vessels, somewhere around the neck, in most cases. However, it is different in case of Inuit people. They have much more active brown adipose tissue throughout their life, which is of course written in their gene. We know specifically which gene it is, what kind of modification. And this is a very strong and very extreme adaptation to such conditions. So brown adipose tissue, BAT, is one of the adaptations, but also morphological adaptations. So in Inuit, they have narrow nasal apertures and relatively long canals, which allows the very cold air to be warmed up. Also, they have very high basal metabolism, and also very low temperature activates blood flow toward their hands and feet. Why is that? Normally, our hands and our feet get cold very easily, and as soon as we get cold, these are the parts that get cold first, because it takes a lot of energy to provide blood and energy flow to these parts. But so it is also some sort of protection mechanism. But why is it on the contrary in case of Inuits? In case of Inuits, low temperature, like I said, activates it. And the solution is actually very simple. They have very high basal metabolism, so they can afford that. It's not a problem for them to provide this extra energy expenditure. But on the other hand, they cannot afford to lose a limb, to lose a hand, to lose feet. That would mean death for them in case of their lifestyle, being mostly hunters traditionally. So this is why, first of all, their bodies can work like this, and also this is the mechanism. Why is that is happening? Of course, our diets also vary, and we can observe that the people that live in different parts of globe have different diets, not only because other types of food is available, also because it matches well the conditions that they need to live in. But in case of Inuits, their diet is quite extreme. Okay, no fresh vegetables, and of course now it's a little bit different. But naturally, they had to base on meat and fat. So it seems like a very unhealthy diet. On one hand, it provides a lot of calories, but on the other hand, it's extremely hypoglycemic. So you're in a state of permanent ketosis, which is not normally it would not be healthy for any Caucasian person, and it's not without consequence for Inuit people. So they have internal mechanisms, also genetic mechanisms, that allow them to metabolize this fat and live in this permanent ketosis better. We wouldn't be able to survive like that, not for a long time. But the price or the consequence is that they're mostly of short stature. They have short necks, and they also have like very stocky build, which also helped them. This stocky build helps them to live in extreme cold mostly, because the larger the surface, the faster body heat will be lost to the environment. So it's better to be bulky and have shorter neck or arms than be very tall and slim and slender if you're living in polar regions. Interestingly enough, there was a discovery that probably we owe some of those adaptations to not only our ancestors, but also other early humans that are no longer here, that did not survive, and that interbred with Homo sapiens, which were Neanderthals, and most probably also so-called Denisovians. Denisovans are very mysterious group, only identified thanks to thanks to finding of a tooth tooth and some other parts, fossil remains, and they're quite a mysterious group, but probably they were interbreeding the Homo sapiens and Neanderthals and Denisovians, and it has left some traces in our genome, including precisely the genes that coincide with very useful mutations that I talked about that can be observed in the Inuit people organism. But I also promised to mention our brave polar researchers. How do they adapt, other than technology, of course? And also I asked the question, is it possible to get used to things, to get used to cold? Because previously we were talking about a long period of time, an evolution that takes its course, and it takes a long time for the mechanism to work. But can you get used to anything in a short period of time? For example, while spending a year in the polar regions as a researcher, right? But surely you know someone who is always cold or is always hot. But there are several examples showing that if we expose ourselves to such factors, to such stimuli, to such triggers, not only our subjective perception of is it cold or is it hot, because we have subjective perception even in being in the same room with the same temperature. Perhaps there is such possibility, but also there is a price to pay for this habit. People chronically exposed to prolonged cold can become accustomed to it, at least to a certain extent, and which does not necessarily have good effects. So typical reactions to hypothermia are shivering, shrinking of blood vessels, and in case if you're triggered by it for a longer period of time, those symptoms of hypothermia are weakened. So shivering is weakened, shrinking of blood vessels is weakened, and the skin surface remains warmer. Unfortunately, Europeans, unlike Inuits or Europeans in the polar regions, for example, in Arctic or especially Antarctic stations, do not have a fast enough metabolism. So they lose heat faster, and they are still at risk of hypothermia because they do not produce enough heat to counteract. So, of course, the body's response is always individual. It may be that acclimatization intensifies the response to cold. Maybe even thermogenesis without even shivering, triggered by extreme cold. There is this classic example, not from the polar regions actually, but from Korea. Amas are Korean women that are pearl fishers, and they are unafraid of the winter sea. They dive all year round, even when the water temperature is even as cold as below 10 Celsius degrees. It is observed that they have a consistent but very reversible increase in their metabolism, their so-called basal metabolism, all the metabolic processes when the body is fully at rest. And just in winter, when the water is very cold, but they still dive for the pearls, the increase can be even 30% of this basal metabolism. Of course, it does not happen immediately overnight. Amas, these women start diving in very light swimsuits in winter at the age of 12, and they continue to do so for decades and every day, even if the air temperature is close to freezing. So they get accustomed to it in time. What about the polar explorer? What about the polar explorers? So the first Scotsman that reached the South Pole. You can see him here on the right. Also the youngest man to reach the South Pole. He was a part of Captain Scott expedition Terra Nuova, which was unfortunately, it ended tragically on the return journey, but nevertheless, he was called Bertie Bowers. I don't know if it's his name. He was a veteran of 20th century polar exploration and was a master of polar acclimatization. He was the hardest traveler who ever made a polar journey and one of the most outdated. He was able to sleep soundly in conditions that made his companions shudder horribly. And every morning he had this routine. Arriving in Antarctica, he stripped naked outside and poured buckets of icy water over himself, much to the horror of his companions. So that it was a very individual feature, we might say. That's it from me.